Alright, so first I hope that your quiz went well. You should have your phone flat on your desk right now, and you should have headphones plugged in so that you can listen to this and not disrupt anyone who may or may not still be taking the quiz. So, yes, the date on the slide is incorrect. That's not today's date at all, but that's okay. I want you to start with a warm-up and pull out your calendar packet, and I want you to do numbers 11 and 13. 11 should be 3 steps long, and 13 should be 4 steps. Okay, so please start that now. You can pause this video, and then when you're done with it, or if you get stuck, you can play them, and I'll go over them in the next 2 slides. So hopefully this means that you are done with the warm-up and you're ready to go over it. So let's start with number 11 and a proof. We always start with our 2 columns and what we're given. In this case, we're given that angle A is congruent to angle C. Okay. From there, we can use the converse of the alternate interior angle theorem, and that tells us that segment AB is parallel to segment DC. Right? Converse always tells us that lines are parallel. Okay, when we're given angles are congruent. So then from there, our last and final step is always what we need to prove, and we're proving that angle B is congruent to angle D, and we get that from this above statement here, okay, by the alternate interior angle theorem. Okay, so alternate interior angle theorem. All right. It also might be helpful to mark the drawing that you're given. It might be more helpful to see kind of how to go down that proof. So if we start with that we're given angle A is congruent to angle C, right? We should then find that AB and CD are parallel, making angle B and angle D the same as well. So next, this should be proof number 13 in your packet. Okay, and again, we start with our 2 columns, right? And number 1 is always what we're given. Okay, in this case, we're given AB is parallel to CD, and that BC, okay, is parallel to DE. All right, so we can mark up our diagram over here and say AB, oh goodness, is parallel to CD, okay, and also that BC, okay, is parallel to DE. Okay, from there, we can use the alternate interior angle theorem. Okay, alternate interior angle theorem. And we can say that angle ABC, ABC is congruent to angle BCD. Okay, so we're talking ABC, this angle right here, okay, is congruent to BCD right here, all right, because we have 2 parallel lines cut by this transversal here, right? So my alternate interior angles are congruent. All right. Next, we can go ahead and say that with our other angles. Angle BCD is congruent to angle CDE because of the same reason, or for the same reason. So we say BCD, this angle right here, is congruent to CDE, or this angle right here, okay, because of the alternate interior angle theorem again. And then step 4, because I told you guys it was only 4 steps, should always be what we're trying to prove, and that's that angle ABC is congruent to angle CDE. I also realize on this slide I don't have the congruent symbol in here, but it should have it in your packet. And so we can prove number 4 by the transitive property of congruence, because we have two angles that are congruent to the same angle, so therefore we can use transitivity. We could also use substitution as long as they're both property of congruence. Notes today are going to cover section 3.5, okay, and that talks all about slopes of lines. So this should not be new to you, but more of a refresher from algebra. So what is a slope? Well, the definition is the slope of a line in a coordinate plane is a number that describes the steepness of a line. So other definitions of slope that you may have used might be rise over run. Rise over run. Okay. Or rate of change can also describe that. Rate of change. Okay. We write slope as this lowercase m, and it equals change in y over change in x. That's what that little triangle stands for. It's a delta, and we just say it as change in y over change in x. The actual formula for it is going to be your y2, or the y-coordinate of your second point, minus the y-coordinate of your first point, over the change in x, which will be the x-coordinate of your second point, minus the x-coordinate of your first point. So here we have every basic slope that you could end up getting. In this first one, right here, this first graph, we're looking at positive slopes, okay, ones that go up. When you're reading a graph, you always read it like you read a book, from left to right. So if it's increasing as you go left to right, it's a positive slope. Opposite is true as you read it from left to right and it goes down, it's a negative slope. Okay. The third one is called a zero slope. Okay. A zero slope just means it doesn't go up or down, right? It's a flat straight line. Okay. And the last one right here, our last graph over here, is actually undefined. Undefined. Okay. And that's because, let's say our point up here was 2, 2. Okay. And let's say our other point that we're using down here is 2, 0. Okay. If we plug that into our slope formula, we take our change in y, which would be 2 minus 0, right? 2 minus 0 over, well, 2 minus 2 gives us 0, and we don't want 0 in the denominator, right? That makes us sad. It's supposed to be a sad face in my 0. Okay, so that gives us an undefined slope, meaning our slope, or our line is completely vertical. Okay, so it's undefined if we have to divide by 0. It's undefined because our line is completely vertical. A reminder here at the bottom is that a fraction with 0 in the denominator is undefined because it's impossible to divide by 0. Okay. For this slide, ideally I would like you guys to find the slopes of these lines. So use your slope formula, use your rise over run, use your change in x over change in y, and find the slopes of all these lines. So if you need to, pause it now, and because I'm just going to keep going and go through what all the answers are for these. So looking at the slope of DC, I'm looking from here to here, D to C. So I'm taking my coordinate D, and my coordinate C is my x2, y2. My coordinate D is my x1, y1. And I should end up with 1 over 6. Okay. Next, for my slope of AB, I'm going from A to B. Okay. You should just be able to see that. You don't need to use your slope formula here, and just see that your slope is 0. Okay. Next we have our slope of AC. Okay, so we're going from A to C. You should see that this is negative, so you should end up with a negative slope. And when you calculate it, it'll be negative 5 over 6. So it goes down 5 and over 6. Okay, and last, for our slope of AD, okay, we're going from A to D. And again, looking at this graph, you should be able to tell that this is an undefined slope because it's a vertical line. Okay. Alright, so here I'm asking us to use our slope formula to determine the slope of these 2 points. Now I'm not giving you the graph, I'm just giving you 2 points. Okay, so when I do this, I'm not trying to be tricky, like whatsoever. When I tell you through J and K, the first point that I give you is going to be your x1 and your y1, and the second point will be your x2, y2. Okay. Sorry, that's my phone alerting me of ESPN. So you'll just use the first point as your x1, y1, the second point as your x2, y2, not trying to be tricky. So we'll take our slope formula, and that is our change in x over our change in y. So we are given what here? So I'm also looking at notes. Okay, so our actual slope formula says y2 minus y1 over x2 minus x1. Okay, so then we just plug in those numbers. So y2 is negative 1, okay, minus y1, which is 1, over x2, which is 2, minus x1, which is 3. So negative 1 minus 1 more leaves me with negative 2. And then 2 minus 3 leaves me with negative 1. Negative 2 divided by negative 1, my negatives cancel, and I just end up with 2 as my slope. Whoops, on that last slide I realized I was saying it fast, and I said x over y instead of y over x. It's always change in y over change in x. Okay, so here we have a story problem, and this is our more real-life version of how you can use slope. In this case, it's really more a rate of change, but it's calculated the same way. So here, Justin is driving home from home to his dorm, and at 4 p.m. he is 260 miles from home, and at 7 p.m. he's 455 miles from home. So we graph this line that represents Justin's distance from home at a given time. Find the intercept. Find and interpret the slope of the line. So we need to pick some points on here. We should probably just use the ones that we were given. So we were given at 4 p.m. he's 260 miles from home. So that's right here on our line. And that will be at 4 p.m. He's 260 miles from home. Okay. And then our second point is right here. And we know that at 7 p.m. he is 455 miles from home. So when we do rise over run, y over x, okay, this again is just our x1